Okay, my presentation is called the Cosmography Forecast with Gravitational Waves using Einstein Telescope. It is part of a paper in preparation by me, Ricardo Surane, and Josiel Mendonça from Brazil. And the motivation for this work comes from the first measurement of the Hubble constant using a detection of gravitational waves with an electromagnetic counterpart by the coalescence of a binary neutral star system. In that case, the precision, the uncertainty in the measurement of the Hubble constant was around 418%. But that is the only detection that we have until now with the combining the detection of gravitational waves and with short gamma ray bursts. So in order to see what is the strength of future detections and detectors to improve the measurement of the Hubble constant and the other cosmographic parameters, I am interested to simulate detections of these kinds of source. So what is cosmography? It is a model-dependent study of cosmological expansion in which I am interested in to constrain the coefficients of the expansion of the scale factor. Each coefficient is related from a derivative of the scale factor, in which the first one is related to the Hubble constant. The second one, called the deceleration parameter, is related to the second derivative of the scale factor. And then we have the other ones parameters. But the scale factor is not unobservable. For the case of gravitational waves, we need to unobservable to perform cosmography in order to constrain these cosmographic parameters, and so explore the evolution of the universe with a model-independent way. So expand the luminosity distance in power series of redshift Z, we get an expansion in which of the coefficients of this expansion are related with some combination of these cosmographic parameters. But the problem is that this series does not converge for redshift larger than 1. In order to avoid this problem, it was proposed in this paper in red here, a new variable for which relate to the redshift, for which expand the luminosity distance in terms of this new variable, we get a series that converge for redshift larger than 1. If you want to see alternative parameterization to do other cosmographic expansion, you can see this reference here. So why use Einstein telescope in order to perform cosmography? The main reason is that with the sensitivity of the current gravitational wave detectors like LIGO, Virgo, and Kegra, we can detect a binary neutral star system up to redshift 0.1 at maximum. In the case of the Einstein telescope, we can go much far. We can achieve redshift up to 6. To detect the coalescence of a binary neutral star system. But we are not only interested in to measure the luminosity distance from the coalescence of binary neutral star. We need also to get the information of the redshift of the source in order to combine the relationship luminosity distance versus redshift in order to study cosmology. In that case, we need to know what will be the electromagnetic detectors that will be in operation joined with the Einstein telescope. One of them will be called the Theseus that will be able to detect gamma ray bursts up to redshift around 10. So you can here in this plot compare the current sensitivity of the LIGO and the Einstein telescope. And the right hand side here, you can see the region in which the Einstein telescope and the LIGO can detect sources with a given total mass and a given redshift with a signal-to-noise ratio larger than 8. In the case for detection of a binary neutral star system, you have this shaded gray region here. And this red point here, you can see the point related to the signal GW170817. And as I said, you can achieve that redshift is 6 with using Einstein telescope to detect coalescent binary neutral star systems. In order to make our simulations of a relationship luminosity distance and versus redshift, we need to know what will be the distribution of this kind of source, not only related to detection of binary neutral star system, but join with an electromagnetic counterpart. So in this paper by Belgas and al., it was estimated what will be this kind of distributions. And you can, that is the green one here, actually it is a fit of the result showing this reference. You can compare this distribution with the current one with the detection of a supernova type 1a and with the detection of gravitational waves using LIGO, Virgo, and Kegra, the blue one here. So by the results shown in this paper, we can see what will be the total number of detection that we can get with 10 years of observations with Einstein telescope and Theseus. In the pessimistic cases shown in this paper, we can achieve a total number of 120 detection up to a redshift 1.5. In the more optimistic case, we can achieve more or less 500 detection during this 10 years of observation with T and the Theseus. Other point that we have to be taking account is what will be the uncertainty in the luminosity distance by detection of this source with Einstein telescope. In this paper by Zhao et al., it was estimated what would be this uncertainty, relating this uncertainty with the redshift. The result in this paper is this green curve here, and you can compare it with the systematic through the gravitational lenses in red one here. And the dominant one will be the instrumental, and you can see the total effect. There is the black dashed one here. You can compare this uncertainty with the current one with a detection of a supernova type 1a, and with the current detection of gravitational waves by LIGO, Virgo, and Kegra. The red point here is related to the supernovas, and the blue one is related to the detection of gravitational waves. And here we can see the expected with the Einstein telescope. And so having this uncertainty estimated and having the distribution that we can see the equivalence of binary neutral star with electromagnetic counterpart, we have how to make our simulations. We start with a fiducial model, in my case is the lambda CDM, and using the uncertainty and the distribution, we get some more data, simulated data like this, using 125%. The next step is to see up to which redshift the cosmography will be reliable. For example, I'm interested to see where the maximal redshift that can use a cosmographic expansion up to a maximum deviation from the fiducial one up to 1%. First, I plot my fiducial model, my luminosity distance obeying the lambda CDM, this black one here in each case, and I will use the expansion, the cosmographic expansion luminosity distance in terms of the redshift Z and in terms of the parameter Y that I showed you before. So plotting this cosmographic expansion in several orders in the intrication of the series, we have something like this. So computing, plotting also the relative difference between this cosmographic expansion and the fiducial behavior of the luminosity distance obeying the lambda CDM, we have something like this, in which if you want to use the cosmography expansion in redshift Z, we can go up to a maximal redshift 0.71, in which we have the maximum deviation of 1% from the original that I will use in my simulations, up to the third order in the expansion. But if you want to use the cosmographic expansion in terms of the parameter Y, you can go up to a redshift 0.77 using the 60th order in the expansion in Y. But with this level of redshift, it is not possible to constrain the parameters S0, L0, and M0. We don't get additional information up to this redshift. So in my project, I used only the cosmographic expansion luminosity distance with respect to redshift Z up to the third order in expansion, up to the jerk parameter here. So this is the cosmological parameters that I'm going to use in my simulations. And the corresponding cosmographic parameters using these cosmological ones here are these 5 parameters here, used to plot the cosmographic expansion in each case. So using this, simulating my data with taking account of the maximal redshift range up to 0.72 and using the uncertainty luminosity distance is expected for Einstein telescope and the distribution expected combined observation of Einstein telescope and the Theseus with for the detection of binary neutral star system. What we are going to do now is estimated what will be the precision in each cosmographic parameter, the first three cosmographic parameters, H0, K0, and J0. For each column are relating to one of these cosmographic parameters. And we have here the dependency in redshift because we start only with one detection. And as I'm increasing the redshift, I'm going far with redshift, I'm increasing the number of detection up to achieve one of these total number of detection. For example, in the case in which I'm interested with the precision in the Hubble constant, the darker line here are related to a total number of detections that I will get with 2,000 detections when I achieve a redshift 0.72. And the lighter case is related to the case in which I will achieve 125 detection when I achieve 0.72. So you can see here in this first row here are associated with that this cumulative distribution that I was showing before, in which I can achieve 120 detection in the pessimistic case with use from 10 years of observation with Einstein telescope and Theseus. In the more optimistic case, I achieve 500 detections in this case. And I also estimated for a much more optimistic case that it is not so good to achieve this level, but I use it to see what we can achieve. In the three first cases, 125 up to 500 detection, we cannot constrain the third cosmographic parameter, J0, but you can see what is the uncertainty that we can get in Hubble constant and compare with the first one using the JW 170817. In that case, I achieve uncertainty of around 14%. In our case, we achieve uncertainty less than 1% with 125 detection. But during the operation of the Einstein telescope, it will be well possible to have another third generation gravitational detectors like Cosmic Explorer or other Einstein telescope in other places of the world. So if we with this third generation gravitational wave detectors, we can improve luminous distance. What will be the effect of this improvement in DL in the precision in the cosmographic parameters? So suppose that with the detectors, we can reduce the uncertainty luminous distance up to 20% of that original one using my previous simulation, my data simulation. So you can see that you can constrain the third cosmographic parameters between 40 and 12% of uncertainty when I go from 125 detection up to 500 detections. And you can see that in the precision of the Hubble constant, you can achieve a precision less than 0.1%. This is very good. But this only if we can reduce the uncertainty in luminous distance up to 20% of the original one. All of the result was made performing 300 realization and getting the average of the relative uncertainty in these cosmographic parameters. So you can ask me if in my Bayesian parameter estimation, we could recover the correct values of the cosmographic parameters related to that one of my fiducial model. In the case of it was the lambda CDM. In computing the bias in each case, I could see that all of the estimated cosmographic parameters are inside 1 sigma around the correct injection parameters with a 90% of confidence level. So these results will be, as soon as possible, will be submitted in arXiv, and this is the results. That's all. Thank you very much.